Hello everybody, my name is Bine Brank, and in this video I will present how we can improve compiler auto-vectorization for ARM architectures using Parallelware analyzer. So I will start this video with an introduction where I will briefly explain scalable vector extension and how we can generate SVE instructions using compiler auto-vectorization. After that I will give a quick overview of compiler directives, a way of encouraging the compiler to perform the vectorization. So this will be demonstrated with two examples, and later on I will present Parallelware Analyzer, a state-of-the-art static analysis tool which recently also became available for ARM architectures. So I will shortly explain how Parallelware works and show a typical workflow when using this new tool. So Scalable Vector Extension, or SVE, is a new SIMD vector extension for ARM architecture. Now, unlike other SIMD extensions, size of the SVE register is not fixed, but rather constrained to a range of possible values, ranging from 128 to 2048 bits. Now, because this size is not predefined in the instruction set, same binary can run on CPUs with different SVE lengths, and this is also known as vector length agnostic code. SVE was designed for HPC, and it contains advanced features which can vectorize complex code structures. Some of these are per lane predication and predicate driven loop control, so this removes the need for scalar remainder code when the size of the loop is not a multiple of SIMD size. Another feature of SVE are also gather load and scatter store instructions, which enable vectorization of kernels with complex memory patterns. And SVE also offers extended floating point operations and a number of vector reduction operations where developers can choose to prioritize speed or accuracy. So SVE environment is already well developed, and the easiest way to generate SVE code is with compiler auto-vectorization. So this is currently supported for compilers as GCC, ARM compiler for Linux, Fujitsu, and Cray compiler. And in order to target SVE, one has to include the flag -march is equal to ARM v8 -a plus SVE and include optimization of level 2 or higher. Now, although compilers are already well advanced in terms of vectorization, there are still a few tricks on how to enable it for some special cases. So sometimes compilers are able to vectorize the loop, but they still decide against that. So two common examples of this are a possible dependency between loop iterations or a negative impact on performance as predicted by compiler's cost model. So in many cases where compiler decides upon vectorizing or not, the developer may have some extra information about the code for which he knows that the vectorization is possible or beneficial. So if that is the case, one can encourage the vectorization through so-called compiler directives. Different compilers offer different directives. However, for the purpose of this video, we will focus only on GCC and on directive pragma GCC IVDEP. So this pragma instructs the compiler that the assumed vector dependencies between iterations can be ignored. So let us now see some examples of this in practice. So in this simple loop, we add the values of a, I plus m, and bi, and store the value back to a of I. So if the value m is less than 0, then this loop cannot be vectorized due to backward dependencies. However, if m is positive, this loop can be easily vectorized. So if the developer knows that m in this case will always be positive, then he can hint the compiler to vectorize this loop. So here I want to show another example where things can go wrong. So here on the left side we have loop S1113 from TSVC benchmark. So in this particular case we need an element a len divided by 2 in each iteration, and it is clear that when loop counter I reaches len divided by 2, the value a of len divided by 2 will be modified, and the next iterations will have to use the new value. Now this means that the second half of the loop has a data dependency, and in this case adding the pragma GCC IVDEP directive leads to a faulty code. So if we see the compiled assembly, we see that in every iteration we load and replicate the element a of len divided by 2. So if A of len divided by 2 changes while computing the sum of all lanes in an SVE register, then we will still use the old version of the value and not a new one. So this example shows that things can go really wrong if this directive is used when it is not supposed to be used. So these are 2 cases where there is possible dependencies between iterations, but we also observed many cases where there is actually no dependency and compilers still do not perform vectorization. So here we see another loop from TSVC benchmark suit for vectorizing compilers. So in this loop we perform a simple multiply add operation if the value b of I is bigger than 0. Now compiling this loop with GCC 11 and targeting SVE, GCC surprisingly does not vectorize this loop, although there are no data dependencies between iterations. So this can be seen in the compiler generated code on the right, which shows only scalar instructions. And changing this loop by prepending it with the pragma GCC IVDEP directive, compiler chooses to vectorize the loop, which can be seen on the right. So here we have tested this particular loop on A64FX processor, and the vectorized version runs roughly 8 times faster than the scalar version. So as already discussed, successful vectorization can have a big effect on the performance, and in order to quantify the effect of this directive, we have applied it on all TSVC benchmark loops. So TSVC benchmark suit comprises of 151 synthetic loops for evaluation of compiler vectorization, and this was done for all the loops where there were no data dependencies between iterations, and for 17 loops this has actually resulted in a significant speed up compared to scalar version. However, adding these compiler directives can be quite cumbersome, especially for real-life HPC applications. So for such cases, a source-to-source transformation tool which would do this automatically would be quite useful, and for this particular case we have chosen Parallelware Analyzer. So Parallelware Analyzer is a static code analyzer which specializes in performance. Now, although Parallelware is still in early stages of development, it has recently also become available for ARM architectures. Now, this tool provides several command line tools and a graphical user interface that leverages the Parallelware artificial intelligence engine for code analysis. So the engine analyzes the code and outputs a performance optimization report with human-readable actionable hints. So while the Parallelware middle end is responsible for the analysis of the source code, the Parallelware backend is responsible for the rewriting of the source code using compiler directives. So this can be done for vector, multicore, and accelerator processors, and it can lead to a significant speedup. Furthermore, Parallelware Analyzer prevents code bugs related to performance by presenting best practice recommendations for parallelization. So here we see an example of Parallelware Report. As you can see, Parallelware analyzes functions and loops in the code, and for each loop outputs a list of recommendations, defects, remarks, and opportunities. So for this particular case, on the picture, Parallelware reports recommendations regarding row major order and non-consecutive array access, and furthermore it displays the opportunity to parallelize loop in line 15 with multi-threading or offloading to GPU. Now let us take a look at how we can use this tool to inject the code with appropriate pragma compiler directives for SIMD. So for this example, we will take a serial version of CG benchmark from NAS parallel benchmark suit. Okay, so first let us see the files in the directory. So typing ls, we see that we have a cg.c main file of this benchmark and 2 header files. Now to invoke Parallelware Analyzer, we first need to use the pw report command. For that we simply write pw report -- summary dot for this directory, and we also need to include the C flags of compiling the benchmark. So in this case, arm v8 minus A plus SVE minus 03, and for this case we also need I common. And here we see the output of PW report. So Parallelware analyzer first reports the number of files, functions, and loop it was able to analyze, and then it gives us the total number of defects, recommendations, remarks, and opportunities. And a very handy feature of Parallelware analyzer is that it always suggests on the next steps that the users can select from. So in this case, let's select the PW check to show us the recommendations which it found in our code. So we can simply copy paste that. And this is the output of PW check. So here, for each particular loop of the cg.c file, Parallelware gives us a list of recommendations for writing better code. So in this case, let's take a look at line 878. It suggests us to consider loop fission to enable vectorization. Or in line 871, so this is a const function, but it is not marked as such. So here at the bottom we have the number of recommendations of each type. Now if you go back again to PW report, here it also suggests us to look at the opportunities for parallelization, which is done with PW loops. So I can simply copy paste this. Oops. And in this case, Parallelware analyzers outputs a table where for each specific loop in the file, it reports whether it was analyzable, what is the compute pattern of this loop. So for example, for all scalar pattern or sparse pattern, which is in here. And in the fourth column, it displays the opportunity for parallelization. So in this case, three different options. One is the SIMD opportunity, then opportunity for multi-threading or for offloading to GPU. So if we take a look at our cg.c file, so the CG benchmark, the hotspot of the CG method is in the matrix vector multiplication, which is seen here in loop 458. So here the outer loop goes over all rows and the inner loop goes over all elements of this row. And as we can see, the Parallelware analyzer suggests us to use multi-threading or offloading to GPU for the outer loop and to use SIMD parallelization for inner loop. So in order for Parallelware analyzer to inject pragma directives into the files, then we can use the pw directives command. So pw directives, and if we want to instruct Parallelware analyzer to inject the SIMD directives for all cases where it finds that this should be done, we can write pw directives -- auto -- SIMD gcc cg.c, and then the name of the new file with the directive. So let's call this cg_pragma.c, and again the list of C flags. So in this case, -march arm v8 -a plus SVE -03 -I common. So here it shows us that it successfully parallelized loop using SIMD. So now if we refresh our directory, we have a new file called cg_pragma. So if we open this file, we see that for this particular case, the pragma gcc ivdep directive was injected. But not only here, but for all loops where it feels that this should be done. Okay, so now we can compile this cg underscore pragma file. So if we write gcc march arm v8 minus a plus sve minus 03 cg pragma, let's see, and let's just generate the assembly, and let's also enable optimization report. So here we see that the loop in line 471 was vectorized using variable length vectors. So this is our, if we go to line 471, so here this loop was successfully vectorized. Okay, so this was a very quick introduction of what can be done with Parallelware Analyzer. So let me briefly present the preliminary results when working with this new tool. So when applied to the TSVC, so test suite for vectorizing compiler benchmark, it successfully identified the need of injecting the pragma for some TSVC loop, which has led to significant speed up, but there were still loops where Parallelware Analyzer failed to do so. So on the other side, no change in vectorization was observed when Parallelware was applied to NAS parallel benchmark suite. So in that case, compiler was able to vectorize kernels without the compiler directives. But since Parallelware is still in very early stages of development, the team is planning to enhance the tool in the near future. So some of the future work will include improvements to the AI engine, incorporation of compiler reports, and support for other compilers. So if anybody watching this video has an interest in testing Parallelware, you have the option to do so for free. You just have to visit the website and apply for a trial version. And so for the end, let me give a quick summary of the work I presented. So as seen, the directives can help to guide the compiler's vectorizations with major performance impacts, and a way to inject these compiler directives could be done with some source-to-source transformation tools like Parallelware. So Parallelware is already available for ARM architectures. So for that, these tools still need further improvement by supporting the developers to add pragmas where that is possible, and to possibly perform more aggressive suggestions when it comes to injecting pragmas. So thank you for watching this video, and I hope to see you using Parallelware Analyzer in the future.